Today we're going to talk about the 7 Millennium Problems, some math challenges that no one has been able to solve yet. These problems are like the black holes of science, points where our knowledge faces the unknown. Solving them would not only expand the limits of mathematics, but could revolutionize fields like computer science, physics, and our understanding of the universe itself. Get ready for a journey to the frontiers of human knowledge. Imagine a giant maze. Finding your way out can be tough, right? Now imagine you have to check if a given path leads to the exit. That's much easier. The P versus NP problem asks if finding a solution to a problem is really harder than checking if a given solution is correct. Simply put, P represents problems we can solve quickly with computers, like sorting a list of numbers. NP represents problems where checking a solution is easy, but finding it can take a huge amount of time, even for the most powerful computers. An example, factoring a large number into its primes. Checking if the factorization is correct is simple, but finding it can take a computer centuries. If P equals NP, it would mean that any problem whose solution can be easily checked can also be easily solved. This would have huge implications for cryptography, artificial intelligence, resource optimization, and many other fields. But if P is not equal to NP, as most mathematicians believe, then there are fundamental limits to our ability to solve computationally hard problems. The Hodge conjecture is like trying to understand a complex sculpture by only looking at its shadows. Basically, it tries to connect algebraic geometry, which studies shapes defined by polynomial equations, with topology, which studies the properties of shapes that don't change under continuous deformations. Imagine a donut. We can describe its shape with an equation, but we can also talk about its hole, which is a topological property. The Hodge conjecture seeks to understand how these two perspectives are related in more complex geometric objects. In more technical terms, the conjecture proposes that certain types of geometric structures, called complex projective manifolds, can be represented by joining simpler geometric pieces called algebraic cycles. If proven true, the Hodge conjecture would provide a powerful tool for studying the geometry of complex objects, with potential applications in theoretical physics, string theory, and cryptography. Prime numbers are like the atoms of math, the building blocks of all other numbers. The Riemann hypothesis, developed by Bernhard Riemann in 1859, is a guess about how these prime numbers are spread out. Simply put, the hypothesis says there's a hidden pattern in how prime numbers are arranged on the number line. This pattern isn't random, but is connected to the zeros of a math formula called the Riemann zeta function. If proven true, the Riemann hypothesis would have huge implications for how we understand prime numbers and how they're spread out. This in turn would affect areas like cryptography, computer science, and information theory. Solving the Riemann hypothesis would be like finding a treasure map in the vast ocean of prime numbers. The Navier-Stokes equations describe the movement of fluids, from water flowing through a pipe to the air moving over the wings of an airplane. However, despite their fundamental importance in physics and engineering, we still don't fully understand these equations. The problem with the Navier-Stokes equations is that they can become incredibly complex when dealing with turbulent flows. Turbulence, which is characterized by chaotic and unpredictable movements, is a common phenomenon in nature. But it remains one of the biggest unsolved mysteries in physics. Solving the Navier-Stokes equations would mean we could better predict and control turbulent flows, which would have a huge impact on fields like aeronautics, meteorology, oceanography, and medicine. Imagine being able to design more efficient airplanes, predict weather patterns more accurately, or better understand blood flow in the human body. Those are just some of the possibilities that would open up if we could unravel the secrets of Navier-Stokes. Elliptic curves are mathematical objects that have fascinated mathematicians for centuries. They appear in different areas of math, from number theory to cryptography. The Birch and Swinnerton-Dyer conjecture, formulated in the 1960s, seeks to better understand these curves by relating their arithmetic properties to a mathematical function called the L function. In simpler terms, the conjecture predicts that the behavior of the L function of an elliptic curve can tell us how many rational points, that is, points with rational coordinates, the curve has. If proven true, the Birch and Swinnerton-Dyer conjecture would have profound implications for our understanding of elliptic curves and their applications. For example, it could lead to new integer factorization algorithms, which are essential for the security of online communications. Imagine a sphere, like a ball. If you tie a rope around it and tighten it, eventually you can shrink the rope down to a single point without breaking it or lifting it off the surface. The Poincaré conjecture, proposed by Henri Poincaré in 1904, essentially asks if the same is true for a three-dimensional sphere, an object that exists in four-dimensional space. In more precise terms, the conjecture states that any closed, simply connected three-dimensional space is topologically equivalent to a three-dimensional sphere. In other words, if a three-dimensional space has no holes, and any loop in that space can be shrunk down to a point, then that space must be a three-dimensional sphere in disguise. The Poincaré conjecture remained unsolved for almost a century, until the Russian mathematician Grigory Perelman proved it in 2002, using tools from differential geometry. His proof was a monumental achievement in the history of mathematics and earned him the Fields Medal, the highest honor in mathematics. The Yang-Mills theory is a quantum field theory that describes the fundamental interactions between elementary particles. It's the foundation of the standard model of particle physics, which has been incredibly successful in explaining how matter and energy behave at the subatomic level. However, despite its success, the Yang-Mills theory still has some loose ends. One of the biggest mysteries is the origin of mass. We know that particles have mass, but the Yang-Mills theory doesn't explain how they get that mass. The problem of mass in the Yang-Mills theory is related to the existence of a hypothetical particle called the Higgs boson. It is believed that the Higgs boson interacts with other particles and gives them mass. In 2012, physicists at CERN announced the discovery of a new particle that matches the properties of the Higgs boson. However, there's still a lot we don't understand about the Higgs boson and its role in generating mass. Solving the problem of mass in the Yang-Mills theory would be a huge breakthrough in our understanding of the universe at a fundamental level. And there you have them, the 7 Millennium Prize Problems. These problems represent some of the biggest intellectual challenges facing humanity. Solving them would not only expand our knowledge of the universe, but it could also lead to new technologies and applications that could change the world. Who knows? Maybe one of you will be the next to solve one of these challenges. If you are passionate about math, don't hesitate to dive into these problems and contribute to the advancement of human knowledge. From DAR Space, we wish you much success in your future challenges. See you next time.